he is going to talk about asymptotic expansions of the integrated density of states.
Thanks a lot. And first of all, I would like to thank the organizers for giving me an opportunity to speak here. And the title is longer than Maria has just read, but one of my goals is to explain what this all means. So it's complete asymptotic expansion of the integrated density of states of multidimensional, almost periodic, and pseudo-differential operators. So all the words I'm going to explain. And I will start from a motivation and give some short overview of the history of the subject. And then I'm going to present the main result. And first I will follow. So I will give some short preview, which is a motivation again. Then the exact statement will require some time to go into detail, and I will try to explain to you what we can and cannot do. And if time permits, I will give some ideas of the proof. Right. So first of all, I should say that this talk is based on a joint result with Leonid Parnovsky from UCL and Roman Sternberg from University of Alabama, and we have a preprint online, which I encourage to look at if you are interested in details. So first, let me start from the motivation, and it is very simple. So in L2 of RD, let us consider a self-adjoint operator H, which is equal to minus Laplacian plus V, where you can recognize the usual Schrödinger operator. And we will assume for a moment that V is smooth and real-valued function, which is periodic with respect to some lattice of periods gamma. And the integrated density of states is classically defined in the following way. So you introduce a function n, which depends on the operator and the spectral parameter lambda, just by count. So first of all, you restrict your operator h to a box with a side length L. So you can take minus L over 2 power d. And for such a restriction, you can put, say, the Dirichlet boundary condition, and then count the amount of eigenvalues for HL which are below the prescribed value lambda. So since you are dealing with an operator on a compact domain with a boundary condition, the spectrum is purely discrete, so this object is finite. But the interesting thing is that if you divide by the volume of the box and then pass to the limit where this size of the box goes to infinity, it turns out that the limit exists, and this is a function which you call the integrated density of states. So, and actually this definition also explains why the name is natural. You count how many of eigenvalues per volume you have for a restriction of your operator, and then you extend the box to the whole space, which does not necessarily preserve it doesn't preserve the property that the spectrum is discrete, but still the object is well defined. And there are some properties which I would like to discuss. So this is just, again, the definition of the integrated density of states. And clearly from this definition, it follows that the integrated density of states is a non-decreasing function of the energy parameter lambda. Indeed, if you count how many eigenvalues are below lambda, then of course the bigger lambda you take, the bigger the chances to count more. The idea exists for any smooth periodic V, and the set, which I have chosen this way, can actually be replaced by a scaled set omega, where omega is just any domain with regular boundary and which has a Lebesgue measure 1 in RD. So this definition is quite robust, and it doesn't really matter how you define the object. It turns out to exist to be the same. And also the Dirichlet boundary condition can be replaced by other self-adjoint boundary conditions, like periodic or third boundary condition, whatever you like. So further properties, the IDS contains information about the spectrum of H. Indeed, if you can actually characterize the spectrum in the following way. Take points lambda for which there exists a positive number epsilon, so that n of h lambda minus epsilon minus n of h lambda plus epsilon minus n of h lambda minus epsilon is positive. so which is just the set of points of growth for the integrated density of states. And it turns out that the spectrum of your operator is exactly this set. So IDS is more than spectrum. So, and if you are thinking of H as a Hamiltonian for some quantum system of particles, and it's natural to think of a crystal because you have a periodic potential, then it turns out that IDS is related to the transport properties of the particles. So you know, for example, that, well, a vague physical interpretation of the spectrum for a periodic system is that you have band gap structure, and bands are where the electrons can be transmitted, and the gaps where are the energies for which your material behaves like an insulator. So IDS actually is related to how good conductor you will have if there is conductance. Well, and what I'm going to discuss today is the high energy asymptotic expansion for the IDS. So if we let lambda big, so what can be said about this function? Actually, physicists have long conjectured that this expansion has the following form. So you have lambda to the power d over 2, and then a series in negative integer powers of lambda, and this series should be accurate to any order. So if you prescribe any k, then the correction to the expansion, so you terminate your expansion at after kth term, and then the correction should be a smaller order than the terms you have calculated. However, what was originally done in the physics literature is just the people tried to calculate the coefficients Ej without actually proving that this expansion is correct. So the standard approach would be just to assume this expansion and try to calculate the coefficients, and this is usually possible. So the first rigorous proof of the Formula 1 in the one-dimensional situation was obtained by Schenk and Shubin in 1987. And this formula is known for a very long time. And only very recently, in dimension 2, it was proved rigorously that indeed such an expansion is correct, whatever k you take. And this was done by Barnowski and Sternberg in two-dimensional situation in 2009. And in three-dimensional situation in, well, it's written here in 2010, but actually the article has just appeared this year. And what I want to stress is that actually establishing the existence of such an asymptotic can be decoupled from the question of calculating the coefficients. It turns out that as soon as you know that some this formula is correct with some coefficients Ej, there are quite efficient methods to calculate the coefficients by comparing your operator with something known. So for example, people know that if you take the so-called heat kernel, so you take your operator h and calculate the exponential function of minus th, where t is a real parameter. Then it turns out that if t is taken to be small and positive, you get the following expansion. So you have just some coefficients aj and powers of t on the right-hand side. And these coefficients aj are so-called heat invariants, and there is a whole bulk of literature where people try to find the best possible formulae for these coefficients. And this can be done, and the answer is that they are given by integrals of polynomials of your potential and its derivatives. And the integrals are, of course, taken over the fundamental cell of your lattice of periodicity. And these heat invariants are ultimately computed by Hitrik and Polterovich and in 2003. Then actually one can relate the formula for the heat kernel with the formula for the integrated density of states. Namely, if you can represent the the average of the right-hand side here as an integral of the integrated density of states with the function e to the minus t lambda. Well, it is quite a natural formula because you can think of well, as I told you already, the integrated density of states is related to the spectrum of the operator. So this is sort of the spectral decomposition of the operator. So it's very natural to integrate functions of the spectral parameter with respect to n and hope to get some functions of your operator, in particular this one. And here m of ij are just the averages of the coefficients here. And this approach was proposed by Karotyaev and Pushnitsky in 2003. So actually, as soon as some asymptotic expansion is established, you can calculate the coefficients quite efficiently. But as I have mentioned already, it's only this year the proof of the existence of such formula has appeared. And well, from this argument, you cannot deduce that n has the expansion you like. All right. So now, if we are more ambitious and want to ask what can be done further, then there is an interesting topic, which are the almost periodic potentials. Namely, this is a popular subject for in one dimension. So in one dimension, well, let me first define what the almost quasi-periodic and almost periodic potentials are. So you call a function quasi-periodic if it is a finite sum of oscillating exponentials. So you just have a trigonometric polynomial with some coefficients. And you say that the function is almost periodic if it belongs to the closure of quasi-periodic functions with respect to the uniform convergence in L infinity. And in one dimension, there are a lot of results where the operators, well, and all these results are reasonably recent, where the operators with quasi-periodic potentials are treated. In particular, well, the experts there are Avila, Bourgain, Eliasson, Zhytomyrskaya, and so on. And people can calculate quite, well, answer very detailed questions about the structure of the spectrum, which turns out to be very interesting. Particularly, you can find that sometimes the spectrum is Cantor, sometimes you can characterize where the gaps in the spectrum are, and you can find both localization and delocalization depending on the energy regime and coupling parameters of your potentials. And it can be proved, for example, that IDS is Hölder continuous. But, well, if you ask, yes, and the asymptotic expansion this one, was established for quasi-periodic operators in dimension 1 by Savin in 1988. But if you ask those experts what is known in multidimensional setting, so suppose your dimension is not 1, it's some d which is bigger, then it turns out that almost nothing is known, except for there is a couple of review articles by Shubin of 1970s, and not much seems to be done since then. And the techniques which all these people are using are quite related to the fact that you are dealing with a one-dimensional operator, which is not surprising. So our ambition is to say something about the asymptotic expansion of the integrated density of states also in this situation. Now, further generalizations, the spectral properties, yes. So Parnovsky and Sternberg have managed to prove the expansion also for d bigger than 1, and the operator being the Schrödinger operator minus Laplacian plus v. But they were not able to treat, for example, the magnetic Schrödinger operators, even in the periodic situation. And this was the main motivation behind the result I am going to present today. So let me just give you some short preview of the main result. If we can obtain an asymptotic expansion of the integrated density of states of self-adjoint operators in in L2 of Rd, which have the following form. You raise minus Laplacian to any positive power you like, and then you perturb it. And the perturbation can be a differential operator or even pseudo-differential operator of order kappa, which is strictly smaller than 2w. So minus Laplacian to the w is the main symbol, and the perturbation is it may be a pseudo-differential operator of lesser order. If B is a differential operator, so like for example magnetic Schrödinger situation, then the conditions on the coefficients will actually be the same as the conditions on V in the Schrödinger case, which was treated by Parnowski and Sternberg. And these coefficients can be smooth periodic or generic almost periodic. In particular, magnetic Schrödinger operators are covered by our results. Well, yes, here maybe I should make a remark. There is some so if you're thinking of potentials or perturbations, then there are two things. One of them one is how your operator behaves in momentum space, which order of differentiation you have there. And the other one is the smoothness of coefficients. And our technique is such that the smoothness of coefficients is much more crucial for us than the behavior in the momentum space. So we can do very general things, and you will see the assumptions what we have on symbols. But the smoothness of coefficients is we need it quite high. Right. So so we are if B is pseudo-differential, then it should be an operator of classical type, which means that its symbol should admit an asymptotic decomposition in powers of modulus of momenta when momenta go to infinity. However, these powers do not have to be integer. And since this is a relativistic program, let me note that the operators of with the relativistic kinetic energy, where you, well, this is the most general non-matrix formula I could think about. So it's minus I gradient plus some magnetic potential squared plus m squared, and you take a square root of it. All such operators are admissible for periodic, or say generic almost periodic, smooth functions A, and masses which are non-negative. You will see that it satisfies all the conditions. For example, it can be expanded in powers of modulus of psi just by, well, expanding this function in the powers of momenta. Right. So now we let me just give you some definition of what pseudo-differential operators are in our case. So you start from a Fourier transform. For any function f, you can calculate this Fourier transform by the usual formula. And our pseudo-differential operators are just those where we take a Fourier transform of your function, multiply it by some function b of x and xi, which is called the symbol of the pseudo-differential operator, and you invert the Fourier transform and get the action of the Fourier of the pseudo-differential operator. And so b is the operator, and little b is called its symbol. And we have to make some assumptions on the structure of the symbol. So first of all, we assume that it is a smooth or almost periodic function in X, and it's naturally assumed to be complex valued. And moreover, for some countable set of frequencies, we require that our function has the following decomposition. It's actually a finite or countable Fourier series. Well, not Fourier series, but a generalized Fourier series. So you have some b hat which depends on theta and xi, and you multiply them by the exponential. So e theta of x are just the functions e to the power I theta x. And the set of frequencies over which you sum, well, you will have some conditions on this capital theta. By now it is just a countable set. So, and the coefficients of this expansion, since we are dealing with almost periodic operators, can be calculated in the following way. You just multiply your symbol by e to the minus I theta x and calculate the expected value in x. The expected value here is with respect to the whole space. So you start from a big box, you average your function in the box, and then you let the size of the box to infinity. So the formal condition for your symbol to be to give rise to a self-adjoint operator is this one, and of course we assume it because we only want to deal with a self-adjoint situation. And under these assumptions, your operator B becomes formally self-adjoint. And now let me specify the assumptions how your symbol should depend on the second variable xi. So for a parameter r, which can be which is any number bigger than 0, and it's natural to think of it being large, we assume well, we define the ball Br as just a set of xi's whose moduli are less than r, and then we assume that for a ball of big enough of a big size, if you multiply your symbol by the characteristic function of this ball in the momentum space, then what you get is a bounded object. So we don't really require any smoothness conditions for xi's which are inside the ball. It's enough that after you multiply the symbol by the characteristic function of the ball, the answer is bounded. And the more interesting requirement we have is outside the ball. So on the complement of this of the support of this characteristic function, we require that you have a decomposition in homogeneous functions of the modulus of xi. So you have some series where the modulus of xi is raised to some powers, and then the coefficients may depend on x and on the direction of the momentum. So of course, this set J should be discrete. It should be bounded above because we want a pseudo-differential operator of finite order. And we assume that this upper bound is strictly less than 2w. So the operator is indeed of smaller order than the unperturbed symbol. Yes, and these functions B, which are now defined on RD cross a unit sphere, are assumed to be smooth, almost periodic with respect to x. And also we want that, well, they can be represented in the following way. So if you look at the decomposition in the second coordinates, so we then they should we should be able to to represent them as convergent series just in powers of the coordinates. So think of it as a Taylor formula in multidimensional situation. And the convergence here should be, well, the series should converge absolutely in a ball of radius which contains the unit sphere in RD. So in a ball of radius bigger than 1. So under all these assumptions, our operator H is will be self-adjoint on the Sobolev space HW of RD, and we are interested in the asymptotic behavior of its integrated density of states as the spectral parameter tends to infinity. Well, but there is a problem here, namely the original definition I've made with restriction to a big domain and then scaling this domain doesn't really apply because you are now looking at a pseudo-differential operator. And for pseudo-differential operators, it's not so easy to restrict things to balls. However, we can propose a different definition. Namely, so since our operator is self-adjoint, we can look at the kernel of the associated spectral projection, which will be a function of lambda and 2 coordinates. And we can calculate this kernel on the diagonal and then the expected value of this function. And then it turns out that this is a good, well, this is a well-defined object. And in the article of Shubin, it was proved that for differential operators, this definition agrees with the traditional one. So at least at the continuity points of this object. So as soon as your operator is differential, you know that this definition is equivalent to the one which I have presented you before. And if the operator is pseudo-differential, let me just define the integrated density of states this way. Right, and it turns out, however, that even the statements like this, so if suppose one operator is bigger than another, then the integrated density of states of A is less or equal than the integrated density of states of B, and non-trivial if you start from this definition. But this all can be proved. So all the natural properties of the integrated density of states can be reproved also if you start from this new definition. In particular, what will be important for us is that if you have an operator A, which is associated to a symbol A depending on x, and well, this D is a differentiation, or you can think of psi, and U is another pseudo-differential operator. And suppose these two pseudo-differential operators have almost periodic coefficients, then it turns out that if you know that A is self-adjoint and U is unitary, then the integrated density of states is preserved under the unitary transformation by U. So if you multiply by U minus 1 from the left and U to the right, then the integrated density of states is preserved. This statement is non-trivial even if you are dealing with differential operators. So without loss of generality, we can assume that our set theta, over which the Fourier coefficients of B are distributed, spans Rd contains 0 and is symmetric. Now I will need 3 more assumptions about my operator, but I should say from the very beginning that if you are only looking at the periodic setting, so suppose you have a periodic Schrödinger or magnetic Schrödinger operator, then all these assumptions which I am going to present now are satisfied automatically. You don't have to think about them. So, but if your operator is, say, quasi-periodic, then they will become meaningful, and in the almost periodic setting, I'm going to explain to you what they all mean. So let me introduce theta k as just k times the sum of theta. So theta is just a set of points on the complex plane. Sorry, not on the complex plane, on Rd. So, and in this set can be added to itself several times, and if I take the k-fold sum, then I call it theta k. So theta infinity is just the union of all theta k's, which I denote by z of theta. So, so z of some set S is a set of all finite linear combinations of elements of S with integer coefficients. So the set theta infinity is countable and is non-discrete unless B is periodic. Right? If B is periodic, then it is just a discrete set, and all the assumptions will be satisfied. So if it is, however, not the case, then we impose the following condition. Suppose you have chosen D frequencies from this set theta infinity. Then the space which you span on these vectors with integer coefficients should be a discrete set, which is a lattice. So why? Yes. So in the periodic case, this condition is just trivial. In the almost periodic case, this condition turns out to be generic. So if right, so what I'm saying, if we are choosing frequencies of B one after another, then on each step we have to avoid choosing a new frequency from a countable set of hyperplanes, and this is obviously a generic condition. Let me just explain what it means. So suppose you are in one-dimensional situation. Then if you, so somewhere you have 0, you have one frequency theta 1, and the second frequency theta 2. I require that any integer combination of these frequencies should be a lattice. So in one dimension, this automatically would imply that this theta 1 and theta 2 are rationally dependent, and then it's a very restrictive condition. It's so imposing my condition A for d equal to 1 is actually equivalent to requiring that the operator is periodic. However, let us look at what happens if you are dealing with a situation in 2 dimensions. Suppose you have one frequency theta 1 and another frequency theta 2. Then the integer combinations will be a lattice which is built on these vectors. So there are all possible points in the lattice, right? As soon as suppose we are looking at which theta 3s can we choose in order to satisfy condition A. So if you choose theta 3 on a direction which goes, say, through 0 and one of the points in the lattice, then it's a dangerous situation. It's equivalent to the one-dimensional question, and then you actually have to require that your new frequency is a rational combination of the original two, which is quite restrictive. On the other hand, if you look at how many directions you have on the plane, then you see that directions which are defined by the points in the lattice are countable. So if you look on the unit circle, after removing the countable set, you still have a very rich set of possible directions. And in these directions, you have no condition about how large the size of your new vector theta 3, say, should be. And then if you have defined several vectors already, then you should look at all possible combinations of vectors you have already defined. And when you are choosing a new vector, still there is a lot of directions where you can choose it without having any condition on its size. So this condition is a little bit nasty, but on the other hand, in generic, in the sense that, well, after removing from the unit sphere countably many directions defined by some hyperplace, you still have a lot of freedom. Right. So if now both theta and j, so j was right. So j was the set of powers we have here, right? If our set of thetas and j's are both finite, then the only condition, which in particular means that your operator is quasi-periodic. You have finitely many frequencies in your potential. Then the only condition we need is A. If, however, one of the two sets are infinite, then actually our technique would be to approximate the original operator with some other operators which have finitely many thetas and j's. And for this reason, we need conditions which describe how well our original operator B can be approximated by such operators with quasi-periodic symbols. In the proof, we are going to work with these approximations of B, and then at the end, we make a continuity argument which will allow us to show that the result also holds for the limiting operators. So for this, we introduce B iota of theta as the suprema of these functions on the unit sphere for a given theta. And then suppose you have a positive integer k, then there must exist R naught, which is bigger than C naught. C naught was the ball which I have cut out, and I have imposed no conditions is inside this ball. So that for every row which is bigger, there must exist approximate set theta tilde, which is theta intersected with the ball of radius rho to the power 1 over k. So you should think of k being large. So this ball should grow with rho, but very slowly. And then you should be able to find a finite subset of j, which I call j tilde, so that the cardinality of this set is also growing with rho, which will be my parameter, but arbitrarily slow in the power scale. And then I require, well, this is a technical requirement, that if I sum my functions B iota of theta with some weights in both theta and r, then the sum over the indices which I have not selected, so I have chosen some theta tilde inside theta and j tilde inside j, and the sum over indices which are not taken should be reasonably small. And the last condition we are going to impose will be a Diophantine condition of the frequencies of B. Right. So again, this condition is only relevant in the case we are going to deal with almost periodic operators. So for quasi-periodic operators, it's all automatic. So we fix a natural number k tilde, and this number will be determined later by how many, how far we are going to go in our asymptotic formula. And we define the set, so theta tilde k tilde. Remember, any set with a lower subscript was just an algebraic sum of the set taken k tilde times, right? So this is theta tilde taken added to itself k tilde times, and we remove 0 from this set. Then actually we call such a set, we say that V is a quasi-lattice subspace of dimension m if V is a linear span of m linearly independent vectors taken from this set. So you have some finite set of frequencies, and you're thinking of all m-dimensional hyperplanes you can span by these vectors. Obviously, it is a finite number because the set is finite itself. And then when looking at all such sets, we denote, the set of all such sets we denote by V, and if, yes, and for any vector, you can project it onto, so given this linear subspace V, we can project any vector onto it and take its orthogonal projection. So you can make an orthogonal decomposition with respect to V. So suppose now we have two such hyperplanes. So you have, you say that these subspaces are strongly distinct if neither of them is subspace of the other one. So think of planes in 3D. We say that two planes are distinct, if are strongly distinct if they say intersect only by a line. The condition is equivalent. This condition that two sets are distinct is equivalent to stating that if we put W to be the intersection of V and U, then the dimension of the intersection is strictly smaller than either of the dimensions of the sets. And now we look at all possible angles which can be obtained by between these objects. Namely, if we have two strongly distinct hyperplanes, then we can consider which intersect by W. We can take orthogonal complements to W in these hyperplanes, and then we calculate the angle between these orthogonal complements. So basically what we are speaking about, we look at all possible hyperplanes and at all possible angles we could get among them. And we will define these angles by, right. So then we introduce a function S, which is the infimum of possible signs of these angles. So we have finitely many objects here, so the infimum is actually a minimum. And then we require that, right. So then we can also look at all possible points which belong to theta tilde taken k tilde times, and take the biggest absolute value of such points and the smallest absolute value of such points. Clearly, since the size of theta tilde was smaller than rho to the power 1 over k, then this r is of the same size. And then we also require that for any fixed k in k tilde, the sets can be chosen in such a way that the smallest sign is bigger than rho to some small to some power which is close to 1, and the smallest vector you obtain is also bigger than some power around 1. So as I said already, actually this condition is only meaningful for almost periodic operators. So if you're thinking of periodic or quasi-periodic operators, don't think too much about what it all means. So, and now let me just say what the main theorem tells. So suppose you have an operator, yes, I introduce this parameter rho, which is the spectral parameter lambda to the power 1 over 2w. And the main theorem will be as this. So let H be an operator which satisfies all the 3 conditions. And for every real number k, there exists a positive L and defined subset J naught inside of J, so that the integrated density of states has this complicated looking decomposition. So what do we have in this decomposition? First of all, well, there are some coefficients multiplied by powers of rho and powers of log rho. And we have an error term, which is any one we like. So for any k, we can make the error term as small as possible. The order rho to the minus k. So what do we have here? The powers of log rho are running from 0 to d minus 1. So there cannot be too many logarithms. On the other hand, well, if you look at the powers of rho here in the decomposition, then they look pretty complicated, right? So they contain d, they depend on the power of the Laplacian you are dealing with, and you have all these possible iotas which belong to my set J naught. Actually, what I make the following remark: the powers of rho, the first expression, there are far too many of them. So, however, many of these powers are spurious in the sense that corresponding coefficients are 0. Because formally, if you look at this expression, it may even happen that this expression is bigger than d if you look at which indices of summation are available there. But on the other hand, clearly, by abstract consideration, you can easily get an a priori bound and show that this can never be true. So although some coefficients, some powers are present here, many of them can be proven to be 0 immediately. And also, if you have obtained the decomposition for one value of k, so the picture is like this. Suppose you have k1 and k2. And, k1 is, say, more negative. So if you have obtained some powers above k2, and you now write the same formula for the remainder of order rho to the minus k1, then in principle, this will give rise to a more dense filling of the real line. And formally, this filling should become denser also here. But of course, just by comparison the answers in both situations, you immediately realize that this here you can never get an extra non-zero coefficient. So, well, as I told you, the motivation for doing this was that as soon as you have any reasonably good formula for the asymptotics, there are sometimes very strong tools which allow you to calculate the coefficients, and even starting from such a general asymptotics as we have, for example, look at the magnetic Schrödinger operator. Then we can just repeat the argument of Hitrik and Polterovich, and then Karatayev and Pushnitsky, and compare with the heat kernel, because the heat kernel for the magnetic Schrödinger operator can be calculated also in pseudo-differential setting. And then it turns out, sorry, not in pseudo-differential, but almost periodic. So if H is a magnetic Schrödinger operator, then all this complicated answer simplifies to a very neat formula, which every physicist would expect, but we are the first to prove. Right. So one immediate and slightly unexpected corollary of the main theorem is the following. So suppose you are dealing now with either operator where B is periodic. B is periodic now, and either it is a differential or pseudo-differential operator of the classical type, as I have defined. Now it turns out that for sufficiently large lambda, the spectrum of H is purely absolutely continuous. Why so? Well, we have already obtained some asymptotic formula. So, since our operator H is periodic, then we can apply the Floquet-Bloch theory to it. And then, actually, one can prove that the singularly continuous spectrum is impossible, and there are two possibilities. Either your spectrum is purely absolutely continuous, or you have eigenvalues, but then these eigenvalues, so it should be infinite. So every eigenvalue will actually have infinite multiplicity just by invariance of your operator with respect to shifts. And then for this reason, if you have such a situation that you have an eigenvalue, then the integrated density of states must have a jump at least of the size of the dual lattice at the point where you have the eigenvalue. But as soon as you have an asymptotic formula which decays at infinity, this can be excluded. And so actually we see that there are no eigenvalues for large lambda if you are dealing with a periodic operator. Right. So it seems that I don't have a lot of time to discuss the proof. So I stop here. Thank you.
Questions?
Yes.
In your expansion, you have logarithmic terms.
Yes.
Do they always appear, or maybe there are some cases where they are absent?
Well, the truth is, in all cases where we can calculate coefficients, they are absent. So we don't have any example where the logarithmic terms really appear. So what happens is, well, this may well be a technical rudiment, which is just related to how we calculate the expansion. And it's an interesting question to find out if there is an example where they are. Because as you have seen, for example, for the magnetic Schrödinger, you can just, by comparing to the heat kernel, find out that the coefficients at the logarithms must be 0, even if formally they are there.
The questions?
In your proofs, is it very important that the leading symbol is somehow rotationally symmetric? So you could have different powers W in different directions? I mean, for the formula, it's obviously important, but...
The proof is quite involved, and the fact that we know the symbol explicitly actually helps a lot. We believe that if you are dealing with a symbol which is uniformly convex, and the chances are you can get the same result. But the problem is, it's really very complicated to calculate. So eventually everything is reduced to calculating some phase volumes. So in the momentum space, you have not so explicitly defined functions. And what we do, we calculate volumes of different domains defined by these functions and show that, well, although we don't know explicitly the coefficients, the answer can be represented as a series in powers and logarithms. And if you go to this generality that your symbol may depend on the direction, even the main symbol, then of course this information which, is much harder to extract. So it may be doable, but it will be quite hard technically.
Any questions? No, thank you very much.